In today's lecture, we will cover analysis of combinational circuits, but the analysis of sequential circuits also follow the same procedure. Analysis is a reverse of design procedure. This you have to basically write expression for function or outputs for a given circuit. And in the next step, you have to draw a truth table. And you have to define logic. Using the table. So for example, we have a circuit with inputs x, y and z. And you can see in this circuit we have basically 3 inputs x, y, z and only one output. Let's say it is f. So at each stage of the circuit and gates we will write expression. For example, the output of let's say this is gate number 1, 2, 3 and finally this is the output from gate number 4. So the output from gate number 1 is, which is AND gate, it is AND of x and y, and the output of gate number 2, which is an OR gate, it is basically OR of x, y and z prime, and the output of gate number 3 is basically the AND of x, y plus z prime with z. You can simplify it. It will be equal to x, y, z plus z into z prime, and this is equal to x, y, z, because z into z prime is equal to 0. And the output of gate number 4 will be OR of x, y, z and y. Okay. So finally you will draw truth table mentioning the inputs and the output. So for x, y, z, f is basically x, y, z plus y. So when when all the 3 inputs are 0, 0, 0, like this, the AND of all 0 is 0 and 0 plus 0 is 0. So f is equal to 0. So when x, y is 0, 0, with AND of z which is equal to 1 and y is 0, we have again 0. Again AND of 0, 1, 0 is 0 and plus y is equal to 1. So if any of the input is if any of the input of this f is 1, then the output will be equal to 1, because this is the OR of y and x, y, z. So here again the function will be equal to 1. So if the y is 1, you can see that your function is OR of y and xyz. Here again y is 1, then the output will be equal to 1. Now we have 1 0 0 plus 0. This will be equal to 0, and this is again 0, so the output is equal to 0. So 1 0 1 will be equal to 0, plus 0 is 0. 1 1 0 plus 1 will be equal to 1. When all the inputs are equal to 1, the output is 1, as 1 1 1 plus 1 will be equal to 1. So in this way you will draw a truth table based on the logic or expression which you have written with the help of this given diagram. So a diagram, circuit diagram will be given, which you have to analyze, and in analysis you have to first write the outputs of each gate and finally the whole output, which is F. The outputs can be 1 2 or 3 or more. Just like in the case of half adder, full adder, we had 2 outputs, and in code converter we had 4 outputs. So for each output you will write this form. Suppose you have 2 outputs, so you will write F1 and F2 here in the table. Okay, so next suppose we have another circuit which is based on the NAND gates only. Suppose we have a circuit of NAND gates. It adds inputs A, B, C prime, so what will be the output in this case? Let's say we have again the output F here. So at each level of the gates you will write the output. The output of this NAND gate will be A dot B whole prime. This is NAND logic. So this will be equal to A prime plus B prime. The output of second NAND gate will be equal to A prime plus B prime dot C prime whole prime. This is equal to A prime plus B prime whole prime plus C. Using De Morgan's law again, A dot B plus C. So now F is equal to AB plus C into B here whole prime. So using De Morgan's law again, we will have AB plus C whole prime plus B prime, and this will be equal to AB prime dot C prime plus B prime, A prime plus B prime dot C prime plus B prime. Using distributive law, A prime C prime plus B prime C prime plus B prime. You can see you can take B prime common here. So this will be equal to C prime plus 1. plus b prime. So this is the final expression for the function f. Now you will write the truth table. A, B, C, defining the inputs, and the output is f, which is equal to b prime plus a prime c prime. So writing all the combinations here. So what will be the value of f for each input? For 0 0 0, we have, you can see from the table, if b is 0, b prime is 1, a prime is 1, and c prime is 1. So the output is equal to 1. Similarly, for 0 0 1, b prime is 1, and anything or with b prime will be equal to 1. For 0 1 0, b prime is 0, and we have a prime 1, c prime 1, so we have output equal to 1. Again, for 0 1 1, b prime is 0, a prime is 1, and c prime is 0. So we have f is equal to 0 0 plus 0 equal to 0. Now for 1 0 0, b prime is 1 and a prime, c prime is 0 1. So again we have output equal to 1. For 1 0 0, again b prime is 1, so the output will be equal to 1. For 1 0 0, we have b prime 0 and a prime is also 0 and c prime is 1. So 0 plus 0 is equal to 0. For 1 plus 1 plus 1, as b prime is 0, a prime is also 0 and c prime is 0, so output is equal to 0. So you can see if there are NAND gates only, NOR gates only, or any type of circuit involving the combination of AND or gates or XOR gates, you will write the truth table in this form, okay, from the given circuit. Next is multi-level NAND circuit, that how you can implement the multi-level circuits with the help of universal gates, and universal gates are NAND gates and NOR gates. Okay, suppose we have a given circuit. Let's say we can take from any circuit from the book, given in the book. Okay, suppose we have a circuit, multi-level circuit. It means that it has more than 2 levels. C, D, B, A, B, C. So you can take a pause and think that how many gate levels are there in this circuit. So please take a pause or think for 1 minute. So you can see these two gates, gate number 1, 2, these are at the same gate level because they have directly the inputs CD and VC. Then again, the output of one is basically the input of the second OR gate. So this is this second gate level. This was the first gate level. This is second gate level, and this is third gate level because the output of second gate level is input of third gate level, and finally this is the fourth gate level. So basically 1 and 1 dash, these are at the same level. This is second, third and fourth gate level. Okay, so now suppose we have to convert this whole circuit into NAND gates. As you know that we can implement any basic logic with the help of NAND gate. To start with an inverter, a single input NAND gate is basically equal to an inverter like this, and for AND implementation we will use two NAND gates in series like this. If this is x y whole prime, again complementing will be equal to x dot y, which is an AND gate xy. Okay, finally the OR logic will be formed with the help of three NAND gates. Here you can see if we have x prime, y prime, x prime, y prime whole prime, it is equal to x plus y using De Morgan's law, which is equal to OR gate. Okay, so what we will do is we will replace every logic gate with its equivalent NAND gate. For example, we will eliminate this gate number 1, and we will draw its equivalent NAND logic, which is basically two NAND gates in series. Now we will eliminate the second gate, which is basically the OR gate, and we will draw the equivalent of NOR gate, OR gate, like this. And again we have an AND gate. We will draw its equivalent. Two NAND gates in series for this OR gate. And finally for this AND gate. We will have two NAND gates in series. So the last step is that you will eliminate the unnecessary NAND gates which are on one line. For example, look at these NAND gates. If the output of this is x, this is x prime, and this is again, the output of this is again x. So there's no need of putting these two NAND gates, we can eliminate them. And similarly, these NAND gates are also one line, we can eliminate them, and these NAND gates also. So we will remove these ones. And we will draw the direct connections after eliminating them like this. Okay, so in this way we have this resultant circuit with NAND gates only. Similarly, you can implement any logic circuit with the help of only NOR gates. For example, we have a multi-level circuit like this, and we have to implement it with the help of NOR gates only. You know that any logic can be implemented with the help of NOR gates also. Starting from the inverter, for OR logic we have two NOR gates. This is equal to x plus y whole prime, and this is x plus y. So this is equal to OR logic. Similarly, for AND, they will use three NOR gates. This is x prime, this is y prime, this is x prime, y prime plus y prime whole prime. This will be equal to x dot y. Simply an AND gate. Now again we will follow the same procedure. We will replace these gates with their equivalent NOR gates. For AND gate, we have three NOR gates like this. Again we will replace the AND gate with equivalent NOR logic, and for OR gate we have two NORs series. So this OR gate will have another input which is Z. Finally we have this AND gate Now we will eliminate the NOR gates which are on the same line, like these. You can see these are on the same line, this one also on the same line, so we can simply remove them. Like this, and we have our resultant circuit with the help of only NOR gates. So in this way you have seen that in chapter number 3 we basically implemented the two level circuits with NAND and NOR gates by converting them into first converting the function into sum of product of sum form and drawing two level circuit for each function. But in this case you have seen that we can also implement multi-level circuits with the help of NAND and NOR logic by simply replacing each gate with its equivalent logic circuit. Okay, so in so far we have completed the chapter number 4.